Calculus. This is John Whitaker for the Probability Graduate Level class, and I believe this is our 25th video lecture. It's going to be a longer lecture. It may be considered to be our 25th and 26th video lectures. I'll just combine them. We might consider it that way. And today what we're going to be talking about is probabilities associated to a random graph being connected. So what I plan on doing today is talking about a graph, a random graph, what it means for a graph to be connected. I'm going to do examples. I'm then going to look at an important lemma that's associated in helping us determine whether the probability of a graph, a random graph, is connected or not. Okay, so without further ado, let's start off with a definition of what it means to be a graph. So a graph consists of a set V of elements called nodes. They can also be thought of as vertex, or vertices. And a set A of pairs of elements of the called arcs. Okay. They're also sometimes known in graphs as edges. Okay. So that's what they are. Pictorially, we represent graphs by drawing circles. To represent the nodes, and drawing lines between nodes that represent arcs. Where, I'll just say that. Okay? And so you would draw an arc, if there exists, you draw a line between nodes I and J. If there was an arc I, comma, J. So here as an example, we have maybe V is equal to the set of nodes 1, 2, 3, 4, and 5. And we have the arcs represented by these tuples. Let's say 1, 3, 2 and 3, 1 and 5, 2 and 4, 2 and 4, and then 1 and 1. That's what I got. So pictorially, here's what I'm going to have. I'm going to draw it this way. I'm going to have 1. Let's make it a little. So here's node 1. Here's 2, 3, 4, and here's node 5. Okay, so those are the vertices involved. I've got them numbered and labeled or numbered. And then there's an arc between 1 and 3. So I'm going to draw a line between those two, a curve between those two. Then there's one between 2 and 3. So I'm going to draw a line here. And even though it says 2 to 3, that's the same thing as 3 to 2. We're not going to put any directions on our edges here, on our arcs. It's not what's known as a directed graph. You can't have such things as directed graphs. Okay, 1 to 5. That's the same thing as 5 to 1. 2 to 4. 2 to 4 again, that's another curve here. And then 1 to 1, we have a curve like that, next 1 to 1. So that's my graph that's represented by these vertices in that arc. That's a pictorial representation. One thing to notice is that 1 to 1 arc is there. So we'll give a special name to that. So it's a definition. I, I is called a self-arc or self-loop. Okay. And we just saw that in the previous graph from 1 to 1, the node 1 to 1. So, the next thing we want to talk about is a path. So in a graph, there exists a path, so I'm defining what path is, between nodes I and J. We're thinking I being different than J. If there exists a sequence of arcs, so I should say a sequence of nodes. Really, the arcs are what's important here. Sequence of nodes. I sub 1, I sub 2, all the way up to I sub k, and then j, such that you can go from I to I sub 1, that's an arc, and then you can go from I sub 1 to I sub 2, and then you can go all the way up to I sub k minus 1 up to I sub k, and then finally you can go from I sub k to I sub j. There's that arc. Those are arcs in the graph. All right, let's look at an example. In a second, okay? We're next going to define what it means for a graph to be connected. If there is a path between each of the n choose 2 distinct pairs of nodes, we say that the graph is connected. All right, so let's look at some examples. So pictorial is the way I'm going to represent them. So here's 1, here's 2. I've got an arc between them, and here's 3 and 4. So in that example, this is a connected graph. And the reason is, it's between any two nodes that you pick, there will be a path between them. So here, if I pick 1 and 2, there's a path between them, of one particular arc. If I pick the nodes 2 and 3, that's nodes that I could pick. Is there a path between them? Yes, there's a path between 2 to 1, and then, arc from 2 to 1, and then from 1 to 3. And so that's a path from 2 to 3. And so no matter which of these, out of these 4 nodes that we have, no matter which 2 we pick, okay, there will be a path from those 2 nodes. Okay? So 4 choose 2, that's 6 number of parents that we could pick. There will be a path between each one of those parents. Okay. Here's another example. So if I just have 1, 2, 3, 4 right here, that's my graph. This is disconnected. That is not a connected graph. Again, that's easy to see. There are 4 nodes here as well, and if you take the pairings 2 to 4, there isn't a path that connects 2 to 4. No path exists between 2 and 4. So far, there hasn't been any probability involved. Well, it's time for that to change. Okay. So here's a definition. A random graph is a graph with nodes v equal to 1, 2, all the way up to n, and arcs A equaling to I x of I, where I runs from 1 to n, where x of I, we can think of them as just one random variable for each I, okay, are independent random variables such that the probability of x sub I equals to j equals to 1 over n, where j equals to 1, 2, 3, up to little n. And what we're going to be interested in the probability that a random graph with n nodes is connected. That's what we're going to be interested in. And we're going to compute that with some conditional probabilities. Okay, so I'm going to write this down in just a second, but before I leave this, what we think of for a random graph, and I'll write part of this down. Look, a random graph's got n nodes in it, and we can think of it like a random experiment. Okay, so you roll a dice. Okay? You have an outcome. Okay, and each one of the outcomes are equally likely to happen. So here, an outcome for a random graph is where you have these n nodes, and that from each node you have an arc connecting it to a node, maybe even itself. Okay? And for each arc that's created from a node, and there's only one arc coming from a node, if you will. Even though we said earlier we're not going to be talking about directed graphs, we're making the arcs that are involved in outcome from a random graph. We're just going to have one from, an arc from each of the nodes. And so here, where the ith node is sent to, if you will, by this random variable, the arc is created, the edge is created, they are equally likely to go to any node. That's what's happening. Let me write some of that down. So in forming a random graph, from each node, I, we select at random one of the n nodes including I itself, and join the ith node with the selected node. With an arc. Okay. So here are some examples. So if I look at, let's call it A. 1, 2, 3, 4. So I'm looking at a graph that has 4 nodes. And I say, oh, okay, 1 and 2 have an arc between them. I'm thinking 1 goes to 2. 2 goes to 3. 3 goes back to 1, and then 4 goes to 3 in this manner. This is possibly, okay, could be, this could be an outcome of a random graph that is connected. Okay? So this is an outcome of a random graph that is connected. Okay? I would say it's possibly, because I don't know what the chance is that each node is sent to any other node as being equally likely. But if that were true, then this would be an outcome for a random graph, and it is connected. Another example, called B, is if we have 1, 2, 3, and 4. Okay, so we have 1 and 2 being an arc between them, an arc between 2 and 3. So I'm thinking 1 got sent to 2, 2 got sent to 3, and then what we have is 4 got sent to itself loop. Now this is not a possible outcome for a random graph. So it's a graph, but it isn't a possible outcome for a random graph. Okay? So random or outcomes for random graphs have exactly n arcs, n number of arcs, okay? Of course, this particular graph is not connected, but it's not even a random graph. For part C, as an example, we have 1, 2, 3, and 4. See here, in this previous example, 1 could go to 2, 2 is sent by another random variable to 3. 3 isn't sent anywhere, and that's what makes it a non-random graph, outcome for a random graph. Here, if I have 1 goes to 2, 2 goes to 3, 2 goes to 1, 3 goes to 2, and 4 goes to 3, this is a possible outcome of a random graph that is connected and let's look at one more example with 4 nodes. So, part D, we have 1, 2, 3, 4, and 1 goes to 2, 2 gets sent back to 1, 3 gets sent to 1, and 4 has a self-loop. This is a possible outcome of a random graph that is connected. All right. Well, I said we were going to compute the probability that a random graph is connected. Got lots of outcomes. And so we're going to look at a construction to help us with that. So let me write that down. So in order to determine if a random graph within nodes is connected, we will look at the following constructions. It's something called a supernode. That's what we're working towards. Something called a supernode. I'm going to leave a little bit more. Let's go. So, starting with some node, say I sub 0. So we've got n nodes to start with this one, we call it I sub 0. We note And for us, I will start with 1 every time. No, but 1. We know the sequence of nodes. Okay. So here's the way we have the sequence of nodes. I sub 0, the first node. Then where is it sent by our random variable? And then we can say, well, what if we apply that random variable twice? So really, that's where x of I sub 0 is sent. That's the node associated with that. And then here we could have x of I sub 0 raised to the 3rd power. And we keep going, where I'll say x of I sub 0, I'm going to say raised to the, let's call it to the k power, just to give it a name. Well, let's call it to the n power to give it a name. I call it n nodes, huh? Let's call it to the k power for a second. We'll use n. It doesn't match the number of nodes, okay? Let's call it k so it doesn't match the number of nodes. Is equal to x applied to x raised to the k minus 1 of I sub 0. Then here's what we're going to find. We're going to let n be defined, it's a random variable, to be the first, you know what, let's change this to n, just in terms of notation. Let's make it n minus. Change it, okay? So n, big N to be the first k such that, so it's 3rd power, such that x to the k of I sub 0 is not a new node. So that's the along in our sequence is the spot in our sequence where whatever's there, the node that's there, has already been repeated. Okay? Okay, so we'll look at an example of that for what big N is. As an example, okay, we have 1, 2, 3, 4. Okay, 1 is being sent to 2, if you will. 2 is being sent to 3. 3 is being sent to 1, and 4 is being sent to 3. So if we consider I sub 0 equal to 1, the node 1, let's just take 1. Then x of I0 is equal to x of 1, and x of 1 is equal to 2. So x raised to the 2nd power of 1 is really x applied to x of 1, which is equal to x applied to 2, and where does x send to? It sends it to 3. Also, x raised to the 3rd power of 1 is equal to x applied to x squared of 1, but x squared of 1 we've just found to be equal to 3. So it's x of 3. And where does the random variable send 3? It sends it to 1. And 1 was already in our sequence. So we have 1, 2, 3. And then 1 is being repeated. So k equals to, so n equal to k equals to 3. It's the 3rd application of x. Doesn't have to do with the node, okay? Now, to obtain the probability that a random graph is connected, we condition on n. So what we have is a probability by previous fact that a random graph is connected. And again, it's a random graph, let me say this, with n nodes is connected. And I'll stop writing down all those words. That's equal to a sum, if you will, as k runs from 1 to n of the probability that the graph is connected, given n equal to k times the probability that n equals to k. Okay, so we're given that n is equal to k. Okay, that's what we're looking at. So let's concentrate on that for a second. Now, given n equals to k, the k nodes I sub 0, x sub I sub 0, x squared of I sub 0, all the way up to x to the k minus 1 of I sub 0. All right, are connected. So the x raised to the k, let's don't forget that, is one of these already listed. But we'll just have this, and they're connected, just this list, one short, are connected to each other. Okay, the x of k one is one of these, so this one is sent to one of these previous ones. Okay, this node is sent to one of the previous ones in this outcome random graph. Okay, and there are no other arcs coming out of these nodes, except to each other. Okay? So they're not going to anywhere else. Okay? I'll say a little bit more about that. So there's no arcs coming out of these nodes. And what I mean is there's no arcs coming out to these nodes to any other nodes. Now, there may be some arcs coming in. And for it to be connected, there needs to be some arcs coming in from other nodes. Okay, we consider these k-connected nodes it's just like one node itself, okay? Called a supernode. Except we know that it's connected to itself as a, if you will, self-loop. Okay, so a supernode is what we'll call it. And we consider the graph having one supernode. Okay. And now the whole graph had n nodes, and so k of them are combined to be a supernode. And so there are n minus k of them that are not part of the supernode that we'll call ordinary nodes. Okay. And each one of these ordinary nodes has an arc coming from it, so from each ordinary node. Okay. Note the probability of a particular ordinary node, so for a random graph, having an arc to a supernode, okay, having an arc to the supernode. So let me think about this before I write something down. Let's all think about this. So look, there are k nodes in the supernode. So this should be k over how many ever nodes we have, which is n. That's correct. So there's k in the supernode. It could go to any one of those nodes that comprise the supernode. So there's k of them that can go to out of the n possible nodes that can go to, where either each one of the n possible nodes are equally likely to be where the particular ordinary node goes to. So, in order to progress to a solution, okay, we examine the following lemma. So this is in our text. Which helps us when considering supernodes. Okay. So here's the lemma. It says, given a random graph, so consisting of, so it's a random graph, but we can write it in a certain way, okay? Consisting of nodes 0, 1, 2, all the way up to R. So in some sense we're saying we're having R nodes, but and arcs given by I running from I to Y sub I, where I goes from 1 to R. So here, remember we're supposed to have in a random graph we're supposed to have the same number of nodes as we have arcs. And right here, this is R arcs, but we really have R plus 1 nodes. So 0, 0 is an arc. Okay? In 0, 0 being an arc is the supernode arc. Okay, so 0 is like the supernode. Then for any fixed natural number k, here's what we have. Okay? Y sub I is equal to J with probability one over, here it's R plus K, okay, and J is equal to 1 to R. That's one of the regular nodes. So the chance that you get sent to a regular node is 1 over the number of regular nodes plus K, where we're going to think of K being the number in the 0, which is the supernode. And 0 going to the supernode with probability, okay, it would be K over R plus K. Okay? All right, so that's our situation. And what we're going to say is, what's the chance that this type of graph is connected? So the probability that the graph is connected when we're in this situation equals to K over R plus K. Okay. Now we want to prove this lemma. The way we're going to prove this lemma is by something called strong induction. So it's an induction proof where we don't only suppose the statement is true for K and have to show it for K plus 1. We assume the statement is true for all natural numbers up to K. But I'm going to, instead of use K, I'm going to have strong induction. The variable is going to be R, consider. Okay, so let R be equal to 1. Then for the random graph, what we call it, really it's outcome of the random graph, to be connected, really it's the outcome of the random graph, to be connected, we only have R equal 1, we only have one ordinary node, so Y sub 1 of 1 has to be equal to 0. And the chance of that happening is K. Okay. So the probability that the graph is connected is K over R over K, right here, so that's 1 plus K, which is equal to K over R plus K, which is what we said the answer should be. So the statement is true when R is equal to R equal to 1. Okay, now we're going to assume by strong deduction the statement is true for all r less than or equal to n. Okay? We must show the statement is true for r equal to n plus 1. So if we have n plus 1 ordinary nodes, okay? Okay, so to compute, the probability is that the graph is connected in the r equal to n plus 1 case. Okay. We will condition on the number of arcs for which y sub j equals to 0. That's what we want to do. Okay, so the probability that the graph is connected. What am I talking about? I'm talking about a graph that has k objects in its supernode, and that we have n plus 1 regular nodes. Okay, so there's n plus 1 plus k number of nodes altogether. This is equal to the sum, right down here, as I runs from 0 to k of the probability being connected, given that exactly I of the y sub j is equal to 0 times, so this is involved with the sum, the probability that exactly I of the y sub j equals 0. So to compute the first part, the first factor in the sum, that is to compute the probability of being connected given I of the, exactly, I of the y sub j is equal to 0. We reason that given exactly I of the arcs, or this is like nodes, are going to 0, okay, and n plus 1 minus I remaining nodes, okay, do not have arcs to the 0 node. So we consider that situation Okay. And so here, when we say this n plus 1 remaining nodes, yeah, we'll just leave it like that. Okay. We can view the situation as having n plus 1 minus I new ordinary nodes and a new 0 node. Okay, so a new 0 node consisting of the old node and the I nodes, the original I nodes, that have an arc to the old 0 node. Okay. And I will prove that that's the way that you can view it. Okay. Now, the probability that a particular one of these n plus 1 minus I nodes, say the Lth one, has an arc to the new node, new 0 node. Okay. So this is like the y's of j's, okay, that were defined in the limit itself. That's the way that I'm proving the situation to be viewed as I'm claiming it can be. Has the right probability. So is the probability that L, the Lth node, is connected. Lth node has an arc to the new 0 node. Okay, let's see. Okay. This is the probability that wait just a second. This probability that L node goes to one of the I nodes that has an arc to the old 0 node. See, the Lth node, it didn't have an arc to the 0 node, okay? And so it has to go somewhere. So to go to the new 0 node, that meant that the Lth one had to be sent to one of the I regular nodes that were sent to the old 0 node. Okay? Okay? And given that L does not connect to the old zero node. Okay. And that's the situation I'm talking about. That's the same thing as the probability that the L node goes to an I that is sent, if you will, to O zero node, and L is not connected to zero. Over the probability that L is not connected to O zero, okay. That's equal to the probability that the L node is connected. It has an R. Okay. To an I node connected, that is connected to the O zero node. Okay. Over the probability that L is not connected to O zero. Okay. This is equal to, okay, so the probability that the L node is connected to a node I, that is connected to the old zero node. Well, there were I of them to a node. I just should say a node because there were I of them, so it's I that were connected to them. And so here we have n plus 1 number of nodes plus k, I think. That's the top part. All over the bottom, this probability is 1 minus k over n plus 1 plus k. So that's the number of ways that L is not connected to the O zero. That's equal to I over n plus 1 plus k, all over here, this would be n plus 1 over n plus 1 plus k. So that's equal to I over n plus 1. And that can be thought of as I over n plus 1 minus I plus I, which would be the situation we're talking about, where we have the number number of nodes in the new supernode being I. Now, that matches the Y sub j type of situation we were talking about before. The probability that the L node goes, that means has an arc, to a new, like this way. Non-new zero node is, so it's the probability that the L has an arc to the non-new zero node, which is equal to the probability, conditional probability. The L node has an arc to the non-new zero node, given the L node does not have an arc to the old zero, which is equal to the probability that the Lth node has an arc to one of the n plus 1 minus I new regular nodes, given no arcs to the old node, old zero node, and that's equal to the probability that the L node has an arc to one of the n plus 1 minus I nodes that we're talking about, one of the ones that aren't single zero, and has no arc to old zero over the probability of no arc to the old zero. And this is equal to, 1 out of the n plus 1 minus I arcs to a particular level, okay? And no arc to the old 0, that there were k of them there, and the n plus 1 minus I. No, it's 1 minus that. That was the chance of getting yes to one of the old. 1 minus one of the old zeros. K minus n plus 1 minus I. So that ends up being 1 over n plus 1 minus I. Over here, this is going to be n. This should be k. Here, this will be n plus 1 over n plus 1 minus k. And that ends up being 1 over n plus 1 minus I plus I. Let me stop there. That's what I write. Okay. And that matches what the y sub j should be. So I'll write down so the new situation matches exactly the situation of the theorem of the lemma, where we have n plus 1 minus I nodes, okay, and k equal to I. So as long as I is greater than or equal to 1, by induction, the probability that the new system is connected is I over n plus 1. Okay, and that's the same thing as the probability that the graph is connected. I'll write it down. Given exactly I of the y sub j is equal to 0. Okay. Now, what about if I is equal to 0?
So if I equal to 0, then the probability of being connected in our sum we have exactly I of the y sub j's equal to 0 is 0, which we could think of is 0 over n plus 1, which equals to I over n plus 1. So it works in this situation too. So in all possible cases, the probability of the graph being connected, the random graph being connected, given exactly I of the y sub j's are equal to 0, is I over n plus 1. So, when r equals to n plus 1, what we have is the probability of being connected to the lemma is equal to the sum as I runs from 0 to n plus 1, probability of connected, given I of the y sub j's equals 0 times the probability that I of y sub j's equals 0. Okay, I won't talk about that. So that's equal to the sum as I runs from 0 to n plus 1, the probability of the graph being connected, given I of the y sub j's equals 0. And now the probability that exactly I of the y sub j's are equal to 0, we have r equal to n plus 1. Let's see, that's going to be n plus 1. You have to choose I, so we think of it as a binomial, so it's times. Think of it as a binomial. Then the chance of success, this has to do with independence, okay? The chance of success of the I when going to y sub j equals 0. That's k over n plus 1 plus k raised to the ith power, where k is the number in your supernote. And then times, okay, so here it will be n plus 1 minus k over n plus 1 plus k raised to the n plus 1 minus I, and that's what we have. Now, this is what we just computed. So this is the sum as I runs from 0 to n plus 1 of I over n plus 1 times this n plus 1. Choose I, k, n plus 1 plus k raised to the I, n plus 1 minus k over n plus 1 plus k to the n plus 1 minus I. Okay, there's some cancellations that can happen. So here, I'll take out the 1 over n plus 1. This is the sum as I run from 0 to n plus 1. Here's an I. What I times, well, instead of canceling, let's just use this quantity here, the sum that we're looking at. So I'm just writing down exactly what we have. And this sum over i's running of this quantity is nothing more than the expected value of a binomial random variable with n plus 1 trials and p, probability of success, given right here, k over n plus 1 plus k. And that's equal to, so that's 1 over n plus 1, so what's the expected value? It's the number of trials, so that's n plus 1 times the probability of success. The probability of success is that k over n plus 1 plus k. And that's just going to be equal to k over n plus 1 plus k. And that is exactly what we wanted to prove for the lemma when r is equal to n plus 1. Okay, so as stated before, the probability that a random graph with n nodes is connected, that's equal to a sum as k runs from 1 to n, probability of being connected given n equals to k. K is the first time we'll get a repeat, okay? Times probability of n equal to k, where, again, n is the first k, where x raised to the k of I sub naught is one of the previous x raised to the m, I'll say, m of I sub naught. And here we have, just let me write right here, where 0 is less than or equal to m is less than k minus 1. Should be equal to. All right. So this is equal to the sum, as k runs from 1 to n of k over n, okay, that's by our lemma. Okay, that's what happens by our lemma, times the probability that n is equal to k. That's by the lemma. And where, for our lemma, r in the lemma is n minus k So this is equal to 1 over n times the sum is k runs from 1 to n of k times the probability that n is equal to k. And so that's nothing more than 1 over n. This part is just the expected value of n. So that's what we've got. Probability that the random graph is connected within nodes, depending on that. Okay, now this is the last thing we need to do to compute the expected value of n, the number of nodes in our supernode. What we're going to do is we're going to define a random variable called I sub I, bunch of random variables, and it's equal to 1 if I is less than or equal to n, and it's equal to 0 if I is greater than n. Based on that definition, it's clear that n is equal to the sum as I runs from 1 to infinity of I sub I. So, thus, the expected value then, which is what we're interested in, is equal to the expected value of this sum, which is going to be equal to the expected value, the sum of the expected values. Okay, and one of the things I should say here is that really, I is changing, okay? And so here, this is nothing more than sum as I runs from 1 to n, little n, because that's the number of nodes that we have. So the chance that big N is bigger than I, once I gets above the number of nodes, is 0, okay? So this is expected value. Can't happen. Now, that's going to be equal to the sum as I runs from 1 to n of probability that big N is bigger than or equal to I. That's what the expected value of I is. The expected value of I sub I is nothing more than the probability that N is bigger than or equal to I. That's definition. Because this is the I sub I is a discrete random variable. So that's what you're going to get for each time. Okay. Now, the probability that n is bigger than or equal to I is the same thing as the probability that x sub I of 0 is different than, well, I will say this way. X sub I of 0, x squared sub I of 0, all the way up to x sub I of 0 squared are all distinct and different from I sub 0 as well. Okay, and that can be thought of as the probability that x sub I sub naught x of I sub naught is equal to j sub 1, with j sub 1 being different than I sub naught. And x sub j sub 1 is different, or is equal to j sub 2, with j sub 2 being different than j sub 1, and j sub 2 being different than I sub naught, all the way up to x. You know, over here I didn't write down the right thing. Let's make a correction. Just looking. Here I wrote down x squared again. It shouldn't be x squared. It should be x raised to the I minus 1. Okay. They're all distinct. So make that change. All the way up to x of I minus 1 is equal to j sub I, with j sub I being different than j sub I minus 1, j sub I being different than j sub I minus 2, all the way down to j sub I being different than I sub 0. Now these guys are independent, so this is the same thing as the probability, the multiplication of x of I sub naught being different than, if you will, well, I'll just say it this way, being equal to j sub 1, with j sub 1 being different than I sub naught, times the probability that x of j sub 1 is equal to j sub 2, with some j sub 2. With j sub 2 being different than j sub 1, and j sub 2 being different than I sub naught, all the way down to this multiplication, because of this independence for the x's, of x here, you know, I could have written this down as x, so the, where would I be? Let me write this down a little differently. So here, x of j sub 1, so it would be x of j sub I minus 1 equal to j sub I. Okay, that's the way I write it down. So here, this is x of j sub I minus 1, x of j sub I minus 1, being equal to j sub I, with j sub I being different than j sub I minus 1, j sub I being different than j sub I minus 2, all the way up to j sub I being different, this should be different, than I sub 0. Okay, so what's the chance that the first guy isn't sent to itself? Okay, well, that's nothing more than there are n minus 1 of them, and it's n minus 1 of them of the nodes that aren't itself over n. And once you know that that's happened, what's the chance that j sub 2 is, x of j sub 2, that node is, x is j sub 2. So j sub 1, I should say, x of j sub 1 is sent to something different than j sub 1 and I sub 1. Well, that means there's n minus 2 nodes that it could be sent to, all of them equally likely to be chosen over here. This would be n. And then times, and we keep going, and we get down to the last one, which is n sub I minus 1 number of nodes out there. So it's plus 1 over n. So there's I minus 1 nodes that can't be. That's equal to n minus 1 factorial over n minus I factorial times n raised to the I minus 1. That's what that is. So finally, here's what we have. The probability that random graphs commit. Remember, it's equal to that 1 over n times the expected value of big N, which is equal to 1 over n. And now the expected value of that big N was this sum, okay, because I runs from 1 to n, of the probability that big N was greater than or equal to I. That's equal to 1 over n, okay, times the sum as I runs from 1 to n of n minus 1 factorial over n minus I factorial, n raised to the I minus 1, because that's what we just computed. And that's a form of the answer. We can simplify this a little bit. This is equal to match what's in the books, n minus 1 factorial. So that n minus 1 factorial can be brought out. I'll pull in the n that's in the bottom inside that sum. So sum as I runs from 1 to n. Here it's 1 over n minus I factorial raised to the n, n raised to the I. And so this is n minus 1 factorial. And let's expand this. So when I is equal to 1, we have 1 over n minus 1 factorial n plus 1 over n minus 2 factorial n squared plus, what would be the last term? Be 1 over, well, it would be 0 factorial n to the n. And now let's rewrite those terms in reverse order, on finite mediums, change the order. And that's equal to n minus 1 factorial. Here it will be 1 over 0 factorial n to the n plus 1 over 1 factorial n to the n minus 1 plus, and the last term we rewrote was 1 over n minus 1 factorial. And then that's all we have, or times n, I should say, into the 1. That's equal to, the sum is n minus 1 factorial, sum as j runs from 0 to n minus 1. Well, let's divide by n to the n here out front. Okay? I'll pull out this n to the n. If I pull out n to the n every time, what I would have is n raised to the j all over j factorial. That's what matches in the factorial or in the book. All right.
Gentlemen, that's all I wanted to show today. Thank you very much for your time and patience. We'll call this lecture 25